Welcome to video number 10 of the Robust Control course. So in our previous videos, we made some reviews about some basic concepts from linear algebra and control systems theory. We talked about the state space representation of systems, and we talked about the similarity transformation. Basically, using a similarity transformation, you can create infinitely many state space models for a system. And then we talked about controllability and stabilizability. So in controllability, if you have a fully controllable system, then every eigenvalue of the system can be changed by applying a full state feedback controller. Whereas if your system is not fully controllable, then some of your eigenvalues will not be affected by feedback control, and those uncontrollable eigenvalues will stay where they are even after applying feedback control. So in this video, I would like to start with a theorem due to Kalman, and this theorem says that controllability and also stabilizability is invariant under a similarity transformation, which means the controllability or the stabilizability property of a system doesn't change with similarity transformation, which is very reasonable, because we know that when you apply a similarity transformation, you don't change the system at all. So you still present the same system, and that means if the system is controllable, then by just applying similarity transformation, you don't change the controllability of the system. And this is quite straightforward to prove. Well, if you say that these are the state variables for your new system, then for the new system, your A, B, C, and D matrix, A, B, and C matrices are shown here. The D matrix matrix doesn't change with similarity transformation. So all you have to do is you construct the controllability matrix by using these new matrices, and you will see that the new controllability matrix can be written as the transformation matrix times the old controllability matrix. And this is because, so let's just review that here. Your A bar matrix is T times A times T inverse. Your B bar matrix is T times B. And your C bar matrix is C times T inverse. Well, for controllability, we don't need the C matrix anyway, but the controllability matrix, first let's write it for the original system, which is B times A times B times, and this goes to A to the power n minus 1 times B. So if you write the controllability matrix for the transformed system, you will put B bar, which will be T times B, A bar times B bar, which is T times A times T inverse times T times B, and this goes away all the way, and the last element will be T A T inverse n minus 1 power of that times B, which is B bar T times B. Okay. Well, clearly this will be identity, and we know we did this before, but this will be equal to T times A to power n minus 1 times T inverse times T times B, and this will be also identity. So in the end, the controllability matrix for the transformed system becomes T times B, T times A times B, and the last element of that will be T times A to the power n minus 1 times B. Okay, so you have T matrix on the left for every element in this controllability matrix. Then you can take T out of the parentheses, and what you will be left with will be B, A, B, A to power n minus 1 times B. And this is nothing but the controllability matrix for the original system with matrices A and B. Okay, so this proves that C bar is equal to the controllability matrix with A bar and B bar is equal to T times the controllability matrix with A and B. Okay, and remember, T is a square invertible matrix. Since the controllability depends on the rank of this matrix, so whatever the rank of the original controllability matrix is, when you multiply it with a square invertible matrix, you don't change the rank of the matrix. Okay, so T is full rank. So when you multiply a matrix with a full rank matrix, the rank of the matrix doesn't change. So that means the rank of the new controllability matrix is equal to the rank of the original controllability matrix, and this means that the controllability of two systems are the same, and this was the point of this theorem. When the controllability matrix is not full rank, which is if it is rank deficient, then we know that it is not fully controllable. That means, as I just said, some of the eigenvalues will be uncontrollable. So the next theorem, which I call the Theorem K2 due to Kalman, is quite useful in that sense. So this theorem says that if the controllability matrix has a rank of k, which is less than n, then there exists a similarity transformation such that with this transformation, the system matrix becomes a triangular matrix where the controllable and uncontrollable spaces are separated. So in other words, the transformed matrix becomes as what you see here in this triangular form, where you have A bar C and A bar C bar. And as you look at the B matrix, the B matrix is also turns into this form where you have some matrix here, but the lower part of the B matrix becomes 0. And if you look at this system, you will see that the lower part, the X2 state, does not get affected by the control input. So the control input only enters the first row, but the second part is affected by its own state and no control input and no control, no first state either. So the second state, X2, is affected by itself only. So which means that that part is the uncontrollable part. So again, with this transformation, the controllable and uncontrollable modes of the system are separated into their own spaces. Okay. And here, the rank is k, so the controllable space has dimension k. So accordingly, this matrix in the upper left part is k by k, and it is controllable. So this matrix is a fully controllable matrix in itself with the corresponding input matrix. Moreover, the transfer function of the system is equal to the transfer function of the controllable part of the system. Okay, so the uncontrollable part doesn't affect the transfer function. So I think it's quite it will be quite useful to observe these things on some numerical examples. You can easily construct some systems yourselves and play with these ideas. And if you are taking the robust control course this semester, I will provide some sample problems in your next homework where you will get to see how these things actually work out on a real numerical example. Okay. So the corollary to these theorems is that since this is the uncontrollable part, if you remember the definition of stabilizability, a system is stabilizable if the uncontrollable part is already stable. In this case, the uncontrollable part is put into this matrix, and the system will be stabilizable if and only if that matrix here is already stable. Okay, so I've left it here as A22, but obviously this A22 is the same thing as that matrix A C bar, A bar, C bar. So if this matrix is stable, then the entire system is stabilizable. This theorem only says that there exists such a transformation. So it is possible to separate the controllable and uncontrollable spaces of a system. But how do you do that? And that is given in the next item as a comment. But remember, since the state space representations are not unique, in fact, you can create infinitely many representations for the same system, the same will be true for the controllable and uncontrollable parts. So in other words, you can represent the controllable part of a system in infinitely many different ways. So let's just take a look at this comment. The comment says that since your controllability matrix is of rank k, that means there exist k linearly independent columns in that matrix. Okay, so you choose k linearly independent columns from the controllability matrix. So these columns span a subspace of the n space Rn of dimension k. I'm sorry, I just somehow I messed it up here. Okay, then you construct an n-dimensional square matrix by adding more columns to these k columns, such that the result becomes an invertible matrix, is non-singular. Okay, so you're just free to do that. So you can choose these k independent columns in infinitely many ways. Likewise, you can add more columns to that to complete it to a full square matrix, and you can choose these additional columns in infinitely many ways. While you're adding these additional columns, the only criteria is that you need to make sure that the full matrix will be non-singular. Then the inverse that matrix you constructed can be used for the purpose of separating the controllable and uncontrollable parts. Okay, so this matrix will satisfy Theorem K2. And likewise, I strongly recommend that you do how these things work out on numerical examples. And if you are a student taking this course, then you will already have to do that in your next homework. When you separate the controllable and uncontrollable parts of the system with this transformation, as the next comment says, we basically decompose the state space into two orthogonal spaces containing the controllable and uncontrollable parts. Okay, so this x1 is a part of the state vector, and x2 is another part, and these correspond to the controllable and uncontrollable parts. So if you come back here, you can take this new state vector and write it in terms of these two vectors, where in the first part you have the controllable part of the state vector and the remaining part is filled with zeros. And in the second part, the first part corresponding the controllable part is filled with zeros, and the rest is the uncontrollable states. So if you look at these two parts, they belong to separate spaces, and these spaces are orthogonal to each other. Okay, that means if you take one column from here and another column from there, their inner product will always give you the zero vector, and it is obvious from here, right? Because this will be multiplied with zero there, and this part here will be multiplied by zero there. So this product will always give you zero, and that's what orthogonality means. So that means this space, the controllable space, and the uncontrollable space, these two spaces are orthogonal to each other. I have two additional comments to make here, comments number 3 and 4. The comment number 3 says that any set of k independent columns of the controllability matrix span the controllable subspace, and the uncontrollable subspace is the null space of the controllability matrix, the transpose of the controllability matrix. So I think this becomes quite reasonable when you consider the transformed system, when the controllable and uncontrollable parts are already separated. So let's take a look at that quickly. So for the transformed system, the system matrices are as shown here. So let's pick up this from here and bring it there. Okay. If you form the controllability matrix by putting B, A, and B like that, it is easy to see that the controllability matrix will be in this form, where you will have in the first k rows, you will have some elements here. So this is populated, but lower part of the controllability matrix will always be 0. That's because you have 0 here. So this BC will have 0 below, and A times V will produce, because of the special form of the A matrix, will also produce zeros below a certain level after the first k columns, k rows. So the controllability matrix will be in that form. So if you take that controllability matrix and take its transpose and multiply it with a vector from the uncontrollable subspace, and the uncontrollable subspace is in that form, right? So it has zeros in the top k rows and some non-zero part below that. So any vector taken from that subspace, and this multiplication will always produce 0. Okay, so this is the transpose of the controllability matrix will be in that form. So it will be 0 here, and there will be some non-zero parts there. And when you multiply it with something like 0 here and some states from the uncontrollable part, this will always be 0, which basically says that the command number 4 is correct. Well, this is for the transformed system where these states are already separated. But even for the original state space model, this will be true. Okay, so if you want to see what the controllable space is, all you have to do is construct the controllability matrix and pick up independent, linear independent columns of that matrix, and that will give you basically a basis for the controllable subspace. And the remaining part will be the uncontrollable, a basis for the uncontrollable part of the system. Next, I would like to talk about observability. Well, we discussed controllability and stabilizability already. So once you understand what they are, observability is very related to that. Okay, so in the case of a controllability, this is your state space model, AX plus BU. The controllability is about how your input can affect your state variables. Okay, so if you can say that by applying control input, you can change the state variables in any way you want, that's what controllability is. In the case of observability, this is the system we consider. X dot is equal to AX, and Y is equal to CX. Well, you can also have a control term here, but that's not really relevant for observability, so it's better we just leave it out. So the observability is about the relation between your state vector and your output vector. So in other words, in controllability, you apply an input to U and you change X. And in the observability, your X changes in a certain way, and by just looking at Y, you can understand what X is doing. So that's what observability is. So it depends on how you choose your output variables. So obviously, if you choose output variables to be equal to X, so this is the full state feedback case, then observability doesn't make sense because you already see what all your states are doing. In the case of observability, you only pick certain elements from your state variables, and that collection of state variables you include in the Y vector. If that allows you to understand what X is doing, then the observability is satisfied. Okay, so this is the system that we have. Your system has n state variables, and you pick an output vector with L elements. So these two matrices, A and C, the system with those two matrices is observable if for any initial condition of the state vector, there is a finite time tau such that the initial condition for the state vector can be determined uniquely from the measurements in the output level that are made from the initial condition up to that finite time tau. So if you observe the output measurements long enough, you can deduce what the initial condition was uniquely. Okay, so if it is possible, then your system is observable. Just like in the case of controllability, for observability, you may make multiple definitions of observability which will be all equivalent. And I have the second definition here. And this definition says that the pair A and C is observable if for any given nth-order polynomial, you can find a gain matrix L such that you can make the characteristic equation for the system with this new matrix be equal to that arbitrary polynomial you picked. Okay, so this also says that, just like in the case of controllability, if your system is observable, then by choosing a gain matrix L, you can adjust the eigenvalues of the matrix A minus L times C arbitrarily. You can locate the poles of this matrix arbitrarily. Okay, so the first definition is very important in observer design, because that definition basically tells you that if your system is observable, then by just using the selected measurements long enough, you can construct the state vector. So this allows you to design observers where you can just measure your output vector, output variables, and by using them you can construct an estimation for the state variables. Obviously there will be some delay. Nevertheless, it is possible to construct state variables by using output measurements, and this is what observers do. And if you look at this, they're very similar in a sense. You can already feel that. And in fact, they are the controllability and observability problems are dual of each other. And what I mean by that is, if you take the pair A and C and take the transposes of that, A transpose and C transpose, and take this as a new A matrix and take this as the B matrix and study the controllability of the system, then the result will be equal to the observability of the system with the original A and C matrices. So that means if the controllability analysis you perform with the transpose matrices tell you that the system is controllable, then that means the system is observable actually. Or if you have stabilizability, the corresponding definition in the observability end is called detectability. So in the case of fully observable system, you can construct all state variables. But if it's not fully observable, then some state variables will not be able to construct it using the output measurements. And if the variables that you cannot see are stable, then you call that as a detectable system. Okay, so because of this duality principle, instead of studying the observability, you can just use controllability tools. You can use the tests for controllability for studying the observability of the system, except that you need to use the transpose matrices here. So that means if you construct the controllability matrix with these transpose matrices, you can see that you can write the controllability matrix as a transpose of this matrix. And this matrix is called the observability matrix. So if you construct this matrix with the original C and A matrices, This matrix is called the observability matrix, and just like the controllability, the rank of it tells you the observability level of your system. The concepts of controllability and observability are very important for any feedback control system, and they will be very important for robust control as well, naturally. So I'm going to end this video here, and in the next video I will be talking about stability and then stability for linear systems, and we will discuss some important theorems that we'll make use of later in this course. So I will talk to you in the next video.